Nowadays, they saw that it was the same learners, they've not yet prepared. And they changed to May. At least some learners, they would have revised here and there. Anything yet on the screen? Is this the problem which I gave yesterday to say screenshot? Was this the problem? Hello?
This one is not the one.
Not the one. This one was between what? It was hydrogen and oxygen.
Yes.
With hydrogen and oxygen. Okay. Temperature, chemical. We're just starting chemical equilibrium. We're not yet far. So, calculation of Kc. This one. This is the one which I said screenshot. Are we agreeing?
Yes.
Roland. So your Kc value which you obtained before we go and rectify, let's see what Kc are you getting. So the Kc should be expressed to the Kc for the water, concentration of water molecules over hydrogen squared, and then the coefficients. All right, the ratio, the initial, the change, and the equilibrium. Then the Kc value, which is calculated here, which is different from yours. Is it the same?
No, it's different.
Value, someone is getting 0.1973, 0.01973, and here the Kc value is 10.67. So let's go to the tables now. Let's go to the table so that we calculate step by step using and correcting your Kc value. So on this one, we are referring to the reaction between hydrogen and oxygen to give you water, isn't it? That is our reaction.
Yes.
Yes, so let's do it in writing. So we are having hydrogen plus oxygen. And this reaction is reversible. Is it a reversible reaction? Yes, or
Yes.
no? Then
Yes.
you have the reaction, 2 hydrogens and 2 here, the coefficients. So 2, 2. Then the reaction is balanced. So let's check the table. Your table and theirs. You see where you missed it. So hydrogen in ratio 2:1:2. So there it's correct. 2:1:2. Even also here. Two is to 1:2. Then initially the number of moles 0.5, 0.5, and 0. Also your number of moles 0.5, 0.5, and 0. So which means this part is still fine. So the only part that we are differing is the change, and that change, it affects the equilibrium as well. So that's where these values are different on the change, where we are getting 0.4, then the other one we are getting 18.2. So let's rectify how those amounts were found. All right, so let's start with the change here. This negative one first. So calculate the amount of oxygen which was used up in the reaction. So we want to see the amount of oxygen which was used up in the reaction. And there was some information that we were told here. There is an information that we were told. We were told that 0.5 moles of oxygen are placed in a 200 cubic centimeter container at 150 Celsius and allowed to reach equilibrium. At equilibrium, so this is what I wanted to tell you. At equilibrium, how many did we find? At equilibrium, we are having how much? 9.6 grams of oxygen at equilibrium.
Yes.
So how many moles are these? 9.6 grams of oxygen.
Oh,
Grams of oxygen. How many moles are 9.6 grams of oxygen?
0.3.
How do you know?
You say 9.6 grams divided by 16 times 2.
So we are having 9.6 grams. So it's 9.6 grams divided by what?
16 times 2.
16, because you are referring to oxygen. So the molar mass of oxygen gas, it means O2. So 16 times 2, which is 9.6 divided by 32. Punch in your calculator, what are you getting?
0.3.
Rounded off or exactly?
Yes. 0.3 exactly.
0.3 exactly. So which means on your table here, which you have, which means you are having the number of moles of oxygen at equilibrium. We are having what? 0.3. So now you work in reverse. You work in reverse. So in other words, you are saying the ones which are there initially, minus this, and I get the ones at equilibrium. So the change, so we are saying the number of moles initially minus the ones that reacted, then I get the number of moles which are at equilibrium. So already I was told the number of moles which are at equilibrium. So the end change here, in other words, it's telling you the number of moles which we can even say which reacted. Make it easy for understanding the number of moles which reacted. So initially, the ones that reacted and the ones which are at equilibrium, 0.3. Is it clear for that step? Isn't it we are trying to identify the mistake? Yes. So 0.3 we were given. This is at equilibrium. So what did I subtract? I subtracted from this initial amount. I subtracted a negative 0.2 moles. Then I get the change. The change, they are being specific that it's a negative, but change, it can be a change which is positive or negative. We can write 0.2 is still fine. So the change was negative, which means we subtract 0.5 minus that, then it's 0.3. Then how do we figure out the other values like 0.4 and 0.1? How do you figure out? Once you have found this negative 0.2, what is your next step? If I'm to ask you, what would be your next step? After getting that, remember this 0.3 moles, we calculated it from the 9.6 grams. So after you get that negative 0.2, what is your next step? Which figure are you going to calculate now? After that 0.2.
We'll calculate the number of moles, changing the number of moles.
How do you calculate it? What do you do? You say what? From that information that we are having. Remember, we have been told initially, what we are having initially, the ratio, how they are reacting, we are getting them from the coefficients of the values. So these figures from the coefficients of the values. Then initially, you don't have products, you only have reactants. So 0 products, reactants, we have been told reactants. Then we have found this value. So which other value should we find in terms of what we are
We
having?
should find the instance and n at equilibrium.
Do you find at equilibrium first, or do you find the change? Where do you go from
change?
The change? Is it the change?
Yes.
Yes, because that's why I am saying this change sometimes it confuses learners. The change is fine, but you can even say these are number of moles that reacted. So this, they are reacting in what ratio? So this is the ratio. So you check the ratio of hydrogen and oxygen. They always react in a ratio of 2:1. So which means if I am having one piece, if one part is 0.2, 2 pieces will be double the amount. So the next step is to double that negative 0.2 times 2. Then I get the negative 0.4 what? 4 moles. Any questions?
No.
And always, the ones at equilibrium, we always say the initial minus the ones that reacted. Then you get the number of moles which are at equilibrium. So 0.5 was initial minus what reacted was 0.4. So they are reacting in ratio 1:2 in ratio. So you don't balance the initial one. The initial ones can be in excess. But how do they react? How do they react? So you check the reaction is double. So 0.2, then you double, you get 0.4 because it's twice in terms of the coefficients, the number of moles, how they are reacting. Then you get that negative 0.4. So when you subtract, it will be negative 0.4 moles minus 0.5 moles minus this one. You get 0.1 moles. So you have found this value after you've got the negative 0.4. So you're about to complete your table now, but we don't have those values on the right. So initially, we are saying we are having 0 moles, but in terms of reaction, check in terms of reaction. You should be also having negative, which means they are being used up. The reactants are being used up to form the product. That's why we are having a plus there. So the number of moles which are reacting. So here we are reacting if 2 moles, here I'm also getting 2 moles. Similarly, if here the ones which are reacting are 0.4 moles, I'm also having 0.4 moles. The plus is just a matter of indicating that these are products which are again negative. It's only showing that the reactants are being used up. Products are formed. Then you have your 0.4. And how do you find the number of moles at equilibrium? Since we said at equilibrium, the system is not going to lose anything, which means everything that is formed by the products, by these products, the number of moles which they are forming, this total number of moles, are producing these ones on the right, 0.4 moles. So that change we are adding. So you don't subtract on the right hand side, you'll be adding that plus. That's why you're also getting a positive number of the number of moles. Any question there in terms of, so you work backwards with this table. Initially, how do they react in terms of ratio? 2:1:2, initial number of moles. The change, which means the number of moles that reacted, and what are the number of moles which are left at equilibrium. So that is the number of moles which are left at equilibrium. Then are you able now to find the concentration at equilibrium? We were told that the volume is what? What was the volume?
200, 0.2 cubic centimeters.
Times 1000 times 10 to the power -3, which means 0.2 moles per dm3. I mean cubic decimeters. So your volume is 0.2 cubic decimeters. So concentration is equals to what? Number of moles over what? Volume. Is it correct?
Yes.
Concentration is equals to number of moles over volume. Right.
Yes.
Which means your number of moles, you are calculating the number of moles, concentration of each. And your volume is not going to change. It's still remaining as 0.2 dm. That is your volume. So then you calculate the volume of each reactant. Concentration of hydrogen, then you square. Concentration of oxygen, we are not squaring, but we divide by the concentration using those number of moles. Not that reacted, but the number of moles were at equilibrium. Isn't it? So which means if you want the concentrations for water, are you getting the same values? The number
Yes.
of moles, the number of moles for hydrogen were 0.1. So 0.1 over 0.2 over 0.2. Then this is just half, which is 0.5 moles per dm3, which is correct. Then you go to oxygen. You check the number of moles for oxygen at equilibrium, 0.3. So 0.3 moles, you divide that 0.3 number of moles over 0.1, 0.2, which is just 3 over 2, which is 1.5. 1.5 moles per dm3. Then lastly, for water, 0.4 divided by 0.2, which is double, twice, 2 moles. So you take the products, so which means hydrogen and oxygen, hydrogen and oxygen. You multiply, then the concentration of products. So they substitute into the Kc, equilibrium constant. So what does the Kc say? The concentration of what over the concentration of what? Kc? It's concentration of what over concentration of what?
Concentration of product over concentration of reactants.
Yes, your concentration of product, then you square it over the concentration
Is
of
H.
Hello. Yes.
Our products is H2O and our reactants are H2 and O2.
What is the product?
Water.
And what is the concentration of product?
2 moles per decimeters.
Yes. 2 moles per dm3, which is cubic decimeters. So is this not the concentration?
It is.
Yes. Then why are we squaring?
Yes.
Because of the coefficient. Is this not our reactant?
Yes.
Right? Is this not our oxygen? Is, isn't it?
It is.
Yeah. So verify if the answer is correct. Let's punch the numbers. Let's punch the numbers.
It's giving me 10.667.
Yeah. So did you identify where your mistake was? It was here where you took the 9.6 and you did not
Yes.
calculate the number of moles at equilibrium. So here you were calculating your concentration. So everything becomes wrong because of which value? Only one value.
9.
Just miss this one. Everything. You'll be just waiting for donation of marks. So that they will be seeing positive marking, but you'd have missed. If you find a marker who is not having a positive attitude, you just mark everything wrong. No matter your process, whatever you've done, where you have showed your. See, even if you missed there, I can see what you are doing, and then I can give some marks. However, you won't get full marks, of course. All right, that was good. Let's at least for trying. So let's move on to the next question. Let's move on to the next question. That was the Kc. So these are equilibrium constant calculations, which was the warm-up. So write the equilibrium expressions for the chemical reactions in dynamic equilibrium. So we are calculating the Kc. So which means the expression, when they say the expression, they did not say the answer, isn't it? Write down
Yes.
the what? Equilibrium expressions for the chemical reactions in dynamic chemical equilibrium. So which means you are simply setting up. If you are given the concentration, how were you going to solve that particular problem? So just leave it as an expression. So you don't have to stress by calculating, hey, so what is the concentration? You just leave it as an expression. NH3, you square, which is the products, concentration of products over the concentration of reactants, hydrogen to the power 3, nitrogen to the power 1, which means you are not no exponent. That is the setup. Then for the second one, where we are dealing with number 1.2, 2 nitrogen monoxide plus oxygen to give you nitrogen dioxide. Then this one is easy, isn't it? Is there any challenge?
Yes.
We are just playing around with the coefficients. And all of them, they are gaseous. And or liquid water, which is gaseous state. But I don't think there was a problem there on the expressions, just an expression for Kc. So a mixture of hydrogen and iodine are allowed to react at 4,480. And then this one should be degrees Celsius. So they did not write the temperature correctly. Hydrogen plus iodine to give 2, which is hydrogen iodide. So the question is now, when equilibrium was established, the concentration were found. Concentration of hydrogen, concentration of art, and then they tell you calculate the Kc value. So let's see how you punch your calculator there. Just a matter of calculator, we see. So we are having the equation for hydrogen plus iodine to give 2. So calculate the Kc given. It's a matter of just substitution here. So we are having hydrogen plus iodine give 2 hydrogen iodide. That is our equation. And remember,
It's giving me 50.17.
Kc 50.17, which is correct. So this one, straightforward, just a matter of punching values. Consider the reaction in the state, reaction in a state of equilibrium. So all of them gases. Then let's work out this one. Let's work out this one. So initially, 4 moles of sulfur dioxide and 2 moles of oxygen were added to 1,5 dm3 container at 300 kelvins. The reaction then reaches equilibrium. So the question is now saying, how many moles of sulfur trioxide are present in the container at the start of the reaction initially? How many moles of sulfur trioxide are present in the container at the start of the reaction?
Yeah.
0. So initially there is 0 then. Okay, so 0 moles. And then the second one. Let's go for the second. For 3.2. If 0.14 moles of sulfur trioxide is formed at equilibrium, how many moles of sulfur dioxide and oxygen are used up in the formation of sulfur trioxide, which means are used up, reacted? How will you go about this one? So solve it and tell me the answers. How many moles of sulfur dioxide? So they are just simply referring to that table, but in an indirect way. It's the same table which they are referring to, but it's just indirect way. So we are drawing that table. You can't work without that table. Needed. You need the table. Are you winning? Are you winning, Rulan? And once you are done with the table, before you answer the questions, please share that table also to me. I want to check it so that you can just take a picture. That's done.
Are 0.55 moles and 0.35 moles.
All right, let's do it one by one. So we want the moles. The question is saying 0.515 moles of sulfur trioxide is formed at equilibrium. How many moles of sulfur dioxide are used up in the formation of sulfur trioxide? So there we are looking for the number of moles in the change, isn't it? Is that
Yes.
not correct? The change.
Yes.
Or the ones which reacted. That's why I say change or the number of moles that reacted. That is what we are looking for here. So that you analyze these are reacting, which means they are being used up to form some products. Okay. So what did you do? You said the answer for sulfur dioxide is what? How many moles?
0.15 moles.
0.15 moles. And then for oxygen, how many moles?
For SO4 is 0.4 and the other one is 0.2.
No, we are answering number A, 3.2A. So you said for sulfur dioxide, 0.15 moles. And now I'm asking, what about for oxygen?
0.15 moles.
It's again 0.15
15.
for oxygen. 0.15 moles. But check the equation. Check the equation as a hint. If
I didn't see it. I hadn't seen the equation.
that is the equation, which is here. Check the equation. Then you correct your answers. So we are
For
not
that
answering.
one, SO2 is 0.15 and for oxygen is 0.075.
Yes, that's correct now. So instead of this, we have it's half, which is 0.075 moles. That's correct. So how many moles are left at equilibrium? How many moles are left at equilibrium? For sulfur dioxide and sulfur and oxygen, how many moles are left at equilibrium?
For oxygen is 0.275 and for sulfur dioxide is 0.55.
And how are you solving it? Initially, how many moles initially were you having? Check the initial moles. Isn't it to use the initial moles to calculate the ones which are left at equilibrium?
Yes.
So instead of 0.55, you have added, isn't it?
Yes.
You don't add. These are the number of moles that what? Reacted. So if something is react, initially we're having some moles. Then when you react that, do you add or you subtract? Initially, this is sulfur dioxide. Initially, you are having 0.4. Then, how many moles reacted? Which means I'm subtracting 0.15 moles. How many moles are left at equilibrium? So the ones which I'm having initially minus the ones that reacted, then the number of moles which are left at equilibrium, those are the moles at equilibrium. So how many moles? You don't add, you subtract. So what answer do you get for sulfur dioxide? the number of moles at equilibrium. These are the initial, this is the change, and the one at equilibrium. That is the one which we want to find for sulfur dioxide. 0.4 minus 0.15, what do you get? (0.4 minus 0.15), what do you get?
0.25.
Yes. So the number of moles at equilibrium for sulfur dioxide, it is 0.25. So do the same for oxygen. Let's do the same for oxygen. How many moles are you getting for oxygen? So which means for oxygen, O2, we have your initial. The ones that reacted or the change, these are the moles that reacted. So the moles which are at equilibrium, then you find the answer, the moles which are at equilibrium. Very simple step. Very simple.
0.125.
Yes. So initial number of moles, how much was there? Initial for oxygen, we said 0.2. And then you subtract the ones that we said reacted, 0.075. Then the ones at equilibrium, you said 0.0.
0.12.
1, 2, 1, 2, 5. Yes. 1, 2, 5. Any question there? Is it difficult? So the one that you are saying, which you are referring to as change. Change is the one that you are referring to as the one that reacted. So the word change, it might confuse you. So that's why I say sometimes I write change or reacted, so that you can give yourself a hint. If something reacts, do I add or I subtract? Yet it's going down, I have to subtract. And for products, the number of moles at equilibrium is the same with the number of moles that are reacted, or which means the change. But initially, you are having 0 for the products. But the number of moles, which is the change, or the one that reacted. So for products, it will be the change. For reacted, it will be only for the reactants. So for products, it's change. That's why it's change or reacted, which means for change, now we are adding. If it's the product, only for the product. And then we have indicated the ones which are left at equilibrium. Calculate the concentration of SO2, O2, and sulfur dioxide. Do you know the volume? What is the volume?
1.5.
And the concentration is equals to number of moles over volume.
Volume.
So now, yes, so you have all your concentration, or all your, for concentration of sulfur dioxide, the number of moles are these ones. The number of moles at equilibrium for sulfur dioxide, we found them at 0.125 at equilibrium. So you have your number of moles, find the concentration of each. The concentration of each. So I want the concentration of sulfur dioxide, the concentration of sulfur trioxide, and the concentration of oxygen. So that we write them down. That's one, the concentration. Say for SO2 concentration is equals to what? Oxygen concentration is equals to what? and sulfur dioxide concentration. Sulfur trioxide concentration is equals to what? Then we are done with that part. Using the formula, number of moles equals to concentration over volume.
The
For
first one is 0.
The first one is
0.167.
The first one is 0.167. Okay. Which is correct, 0.167. But to indicate these are mole dot dm3, which means cubic decimeters. And the other one?
Second one is 0.08. 0.083.
Okay, 0.083. Again, it's mole dm3. And then the last one?
0.1.
That's correct. 0.1 mole dot dm3. Okay, which is correct. Then now we are supposed to calculate the Kc at 300 kelvins. So using this information, let's calculate the Kc. You have your formula, your equation, you have your values, that is the equation on top. Let's calculate the Kc. Tell me what is the value of your Kc.
$4.32.
4.3.
True.
4.32 is correct. Is correct. All right. So this was the table which we were talking about. So the table. So these questions, when you see them, they are asking you where to draw your table. So the one that you are saying change can be changed in the sense of the products. It has changed, but in terms of reactants, it will be something that is reacted. So these are the moles that reacted. So the trick is the number of moles which are at equilibrium are the same that have changed. So once you know the number of moles at equilibrium, these two values are the same. Here, because initially we don't have products, so it's a 0. So already have two values. Then using the reacted, which means once you know it's reacting in ratio, these molecules are reacting in ratio 2:1:2. So 2:2, which means these values are the same. They only differ in the sign to say that here you are going to subtract, but there you'll be adding. That's all. So double or half of 0.15, which means coming from the reaction. To get the ones at equilibrium, just say the initial amount minus this, you get the equilibrium. The initial amount minus this, you get the equilibrium. But for product side, that is why we are saying the change. From 0 to 15, which means the change was a 15. So we don't subtract for products. Okay. And then your Kc value, the concentration which you got were correct. The volumes Kc is the same. The only difference may be because of rounding off here, 0.167, and then the answer is slightly more close, which is correct. That's because of rounding off. So screenshot this one, you work this one. Then we discuss it before we start tomorrow. Screenshot this one. We practice this one. Very easy. Just warm up with that one. Screenshot this one. Yes, screenshot that one. Tomorrow we'll start from there until we are done with the chemical equilibrium. So now we'll be working questions of what we have done. The rate of reaction rate will be just killing the questions, projectile motion, just having more questions, practice. You now know what to do, but you'll be just having more tricks. Organic chemistry, you'll be just having some questions so that you are not forgetting things. Okay. So number 4, we'll start from there tomorrow. Is it fine?
Yes.
Okay, let's stop for today. We'll continue tomorrow.